Hello, my name is Tyler Malloy, and the title of my presentation is Modeling Visual Decision Making Using a Variational Autoencoder. The focus of this talk is in modeling the way that humans make decisions in utility-based decision tasks. An example of this is shown on the right, where an agent is presented with three different options. So in the first option, there's a 50% chance of receiving $100 and a 50% chance of receiving $0, and so on. So one possible way to make a decision here is to choose the option with the highest utility. However, all three of the outcomes here have the same expected utility, so a model that's based on expected utility maximization might predict a random choice between these three different options. However, human decision makers are rarely this strictly logical, and they may be biased by things like risk aversion or risk-seeking behavior or loss aversion and so on. And all of these factors can change the way that a human would make a decision in this task. And the model proposed in this talk will discuss one possible source of deviations from utility maximization, specifically from resulting from humans' natural capacity for processing information. The model described in this talk is based on a variational autoencoder, which is a deep neural network model that takes in as input some stimulus, which can be an image or other input, and forms a low-dimension representation of that stimulus. The model then uses this low-dimension representation to reconstruct the original stimulus as closely as possible. So the network is trained based on the similarity between the original image or input and the reconstructed stimulus. Beta VAEs are a type of VAE that add a term to the learning objective of the model that additionally constrains the informational complexity of the low-dimension representation. This allows the model to balance the accuracy of the reconstructed stimulus with the informational complexity of the model. The first term in this loss function is analogous to the stimulus reconstruction accuracy, and the second term is analogous to information complexity. There is a beta parameter which controls the degree of the information bottleneck. As the beta goes to 0, the model is only constrained by the network structure in an information theoretic sense, and as beta increases, the information bottleneck becomes more constrained. The model we propose takes the beta VAE to be analogous to a working memory model of decision making. In the context of working memory modeling, these low-dimension representations can be understood analogously to a psychological representation of a stimulus. An additional utility prediction module takes as input the psychological representation and tries to predict the expected utility associated with the stimulus. The result is a model that can reconstruct original stimuli in utility prediction tasks as well as predict the utility associated with a stimulus. This is closely related to similar applications of beta VAEs in related tasks such as change detection and categorization. The unique feature of our model is that the utility predictions of stimuli are fed back into the working memory model to train the VAE to form utility-based representations of stimuli. The way that this utility prediction is used to train the beta VAE is by altering the learning objective with a weighted value of the difference between the true utility and the predicted utility. So this includes a utility weight parameter, shown here as epsilon in the learning objective, which alters how much the beta VAE focuses on the accuracy of utility prediction versus the accuracy of the reconstructed stimulus. We're going to show through experimentation that some phenomenon of human economic decision-making, specifically deviations from maximum expected utility, can be understood as resulting from an information-constrained representation of stimuli. The model we describe is applied onto the following decision-making task based on visual information. The stimulus is 2 jars of marbles, and the decision maker will choose one of the jars, and a marble will be selected at random from the jar, with each marble within a jar being equally likely to be selected. Each marble color has a set probability of appearing in any jar that is the same among all examples in the dataset used to train the model. To determine the true expected utility of a marble jar, each marble color has a different utility, and all utilities are averaged to get the utility of the jar. The goal of the decision maker is to choose the option that gets them the best chance at a higher utility. Taking this visual decision-making task as an example allows us to demonstrate the functionality of our proposed model. The working memory model takes the stimulus ground truth as an input and forms a psychological representation of that stimulus. The utility model then takes that psychological representation and predicts the utility associated with the original stimulus. The utility prediction is fed back into the working memory model using the utility-based loss function, and the result is a psychological representation that allows for utility predictions and stimulus reconstruction. Additionally, the internal representations are task-specific due to the utility-based training method, and the aspect of our model is inspired by biological plausibility in that it is informationally constrained, and representations are domain-specific. The information constraint and utility weight can be altered to impact the behavior that is predicted by the model. In our modeling, we are interested in connecting the model's behavior to known deviations from utility maximization that are present in human decision-making. One example is risk-averse behavior, which describes overvaluing decisions that have outcomes with less variance and undervaluing decisions with higher variance outcomes. Traditionally, in decision-making modeling, this type of behavior is explained with something like a nonlinear utility function, such as the one shown here. The utility function is nonlinear in that a given magnitude difference at a higher utility is seen as less valuable than the same magnitude difference at a lower utility. And this is motivated by the general idea that, for example, a single dollar difference in a possible outcome becomes less significant to a decision maker as the amount of money increases. This type of utility function can explain risk-averse behavior as resulting from different weights given to the possible outcomes of an event, such as undervaluing an event if it is both unlikely and very high utility. If an agent were to undervalue an unlikely event with high utility, they would probably display a preference for decisions with outcomes that have less variance. Our modeling results showed that similar risk-averse behavior can be observed through altering the information processing capacity and utility weight of our model without an explicitly nonlinear utility function. This contrasts with previous explanations of risk-averse behavior. The way that this is done was by training multiple models with different information constraints and utility weights on the marble jar selection task. 4 models were trained with and without the utility-based training method and with and without the information bottleneck. Training without the information bottleneck results in a regular VAE, whose results are shown at the top of the figure. And after this, we took a set of marble piles with the same utility but different variances and calculated the error in prediction of utility based on the variance of the jar. In most models, there was no clear correlation between marble jar variance and the predicted utility. However, in the model trained with both an information constraint and utility-based learning objective, there was a correlation that corresponds to risk-averse behavior. These utility prediction errors are shown in blue on the lower graph. This corresponds with risk-averse behavior because the marble jars with lower utility variance are predicted with a positive error, indicating overvaluing, and those with higher variance are shown with a negative error, indicating undervaluing. The source of this risk-averse behavior is due to the specific probabilities of each marble occurring in the jars and their utilities. So one possible explanation is that because the gray marbles are both high in utility and unlikely to occur, the beta VAE model trained with utility-based training is undervaluing them due to the constraint placed on the amount of information used to represent the stimulus. And as a result, the behavior of the model is risk-averse. The next set of results compared the reconstructions of marble stimuli based on information constraints and utility weights. A beta value equal to 1 corresponds with a traditional VAE, And as the epsilon value increases, we're having a utility-based training method. So looking at the reconstructions, we can see that the beta VAE trained with utility-based training on the top right correctly reconstructs the 3 high utility gray marbles. However, interestingly, it switches their location. This corresponds with expectations from human decision-making on this task because the specific location of marbles is irrelevant to predicting their utility. The future direction of this research is to extend the utility prediction module to learning the values associated with the marbles in the marble jar task. This will be done using a reinforcement learning training method in which the RL module will make a prediction of utility and update these predictions based on observations from the task. Reinforcement learning has been used to model human learning in many domains, but it is typically done with tabular reinforcement learning. Tabular RL can be useful for simple environments, but it can require handcrafted features in more complex visual tasks. Neural network-based deep RL can work in more complex environments like video games, but less work has been done on predicting human choice selection in learning tasks with deep RL in tasks with complex visual stimulus. Our proposed model can allow for these types of predictions by modeling how humans form task-relevant representations of complex stimuli and then use those representations in reinforcement-style learning. Thank you. For any questions, please feel free to contact me at the following email.